Picture yourself sitting at a desk the night before a massive final exam. You have a mountain of flashcards and practice tests in front of you, and you are trying to cram as much information into your brain as possible. You're trying to absorb the actual logic behind the answers. That way, when you sit down for the real exam tomorrow, you'll be ready to solve problems you've never seen before. Building an artificial intelligence works exactly the same way. We give the computer a giant stack of practice materials, which data scientists call training data. Then we grade its performance against the unpredictable real world, which we call testing data. And just like human students, AI models can develop some pretty terrible study habits. They can sit in the lab for days with all the right materials and still manage to completely bomb the final exam. Learning to spot and fix these bad habits, specifically two errors known as bias and variance, is a foundational part of making AI reliable. Let's look at the first bad habit. Imagine a lazy student who glances at the practice test, decides the material is way too complicated, and just guesses C straight down the line. In machine learning, we call this high bias. The AI has formed a rigid, overly simplistic view of the world. It refuses to look closely enough at the data to capture any of the actual messy patterns hidden inside. This chart shows exactly what a lazy, high-bias model looks like. We have all these data points following a clear upward curve, but the AI draws a stubborn, straight yellow line right through the middle, missing almost everything. Because it ignores the obvious trend, this straight line fails the practice test miserably. Since it didn't catch the pattern in its study materials, its score on these specific examples is incredibly low. Since the computer learned absolutely nothing of value from the practice data, it is going to perform terribly in the real world too. Data scientists have a name for this fatal flaw: underfitting. Now let's look at the opposite extreme. Imagine a highly anxious student who memorizes every single practice question word for word, down to the typos. We call this high variance. Instead of learning the general rules, the model becomes overly complex. It becomes incredibly sensitive to every random blip and piece of noise in its study materials. This chart shows what happens when a model tries too hard. Notice how the yellow line bends itself completely backward, zigzagging wildly, just so it can perfectly touch every single little crossmark on the graph. Because it hits every point, this model gets a perfect score in the lab. It didn't miss a single question in its practice stack, making it look like a genius on paper. But the moment you take this model into the real world and change a single variable, its performance falls apart. As soon as it sees a question it hasn't memorized before, it fails. This is a deceptive failure. It tricks developers into thinking their AI is ready, only to break apart when faced with new information. And we call this brittle state overfitting. So developers are stuck between a rock and a hard place. You can't rely on a lazy model that underperforms, and you certainly can't trust an overly complex model that deceptively overperforms in the lab. This tension is the bias-variance trade-off. It is the constant engineering quest to find a stable middle ground between ignoring the data entirely and memorizing it too perfectly. The sweet spot we are looking for is a model complex enough to recognize genuine patterns, but simple enough to brush off random noise. This chart shows that ideal balance. The smooth yellow curve traces the true underlying path of the data. It doesn't stress about hitting every single mark, which means it actually understands the assignment. To get a model to behave like this, engineers add a specific type of penalty to the learning process. It's like a teacher confiscating your flashcards mid-study session, forcing you to use your own logic to solve problems, instead of relying on a memory crutch. A successful AI has a flexible understanding of its subject. It is built to move past what it has seen and adapt to the